Good afternoon, everyone. Welcome to this theater session. I'm Yichao Pan, product manager at NVIDIA Robotics. So today I'll be presenting how NVIDIA is accelerating industrial automation. And then I will hand it over to Francois and Jimmy, who will share Vention's experience of adopting our products to accelerate the development of their bin picking solution. And in the end, we will leave a few minutes for questions. So a little about myself. I joined the product management team at NVIDIA Robotics last August. And prior to NVIDIA, I was product manager at KUKA Universal Robots and Resync Robotics, back when Resync was still a robotic startup in Boston. So I have about almost 10 years of experience working in the world of industrial automation. And this is the third year for me attending Automate in a row. And it truly feels home to be back here in Detroit. And today I'm excited to share more about what we are doing in the space. So many people know NVIDIA as a computer graphics company. So you may wonder, why is NVIDIA here at Automate? That's because we're building a computer platform for physical AI. What is physical AI? It means a kind of AI that can actually interact with the real physical world. We believe robots are the best embodiment of physical AI, and we are building 3 different computers for them. The first computer is DGX. This is our data center computer that can be used to train large AI models. And examples include H100 and B200 that are normally used for training large models such as ChatGPT. And the second computer we are building is OVX. This is a computer we are using to power our simulation platforms, such as Omniverse and Isaac Sim. Not only can you design and validate your robotic solutions in simulation, but more importantly, you can use simulation to generate synthetic data to train your own physical AI models. And I'll come back to this in a moment with some real examples. And the last computer is AGX. This is for edge computing. So once you have your physical AI models and ready to deploy them, you can run them on AGX. And a good example is Jetson Orin, which some of you may be already familiar with. You can embed Jetson into your automation controller or robotic controller for real-time performance of AI. So if you're interested in learning more about what NVIDIA is doing regarding industrial automation and robotics in general, please come to the keynote session tomorrow morning at 9 o'clock. Deepu Talla, our Vice President of Robotics and Edge AI, will be delivering a keynote about industrial autonomy in the area of physical AI. But in today's session, I would like to focus on Isaac Manipulator. So this is a collection of AI models, accelerated libraries, as well as reference workflows specifically designed for industrial robot arms. And our mission is to enable developers to develop AI-powered intelligent robots that can interact with real physical world. And this is a mission that deeply resonates with me from a personal level, because yesterday was Mother's Day, and my mom reminded me once again that she's waiting for an elderly care robot that can take care of her when she gets older. And I believe NVIDIA is working on the right technologies to enable robots to be truly intelligent and safely operate in dynamic and household environments. But in the near term, we are starting with the industrial environments, which already have urgent and pervasive problems that customers are willing to pay for. So in 2025, our focus is on solving the unstructured pick-and-place applications in industrial environments. So every manipulation workflow starts with perception. And at the core of our perception stack is a model called FoundationPose. This is a pre-trained foundation model for 60 pose estimation. And 60 pose estimation is very critical for accurate pick-and-place applications because the robot needs to know where the object is, regarding its position and orientation before the robot can actually manipulate the object. To train physical AI today, it's very challenging because there's not a lot of existing data you can leverage. If you are training a large language model like ChatGPT, you can actually use all the existing data on the internet, but that simply doesn't exist for physical AI. So what do you do here? So our research team actually used our second computer and Omniverse Isaac Sim to generate over 5 million synthetic images to train this model. And they did it on our DGX first computer in just a few days. And the result was amazing. We were able to achieve the state-of-the-art performance and very strong generalizability to novel objects. So this model simply works out of the box without any retraining or fine-tuning. So to enhance the performance of FoundationPose, we also have a number of other models. For example, FoundationStereo, this is a new model for zero-shot stereo matching for depth estimation. So what does it do, actually? If you are using a low-cost, affordable camera, such as Intel RealSense, typically you are not able to get very accurate depth map out of it by default. And that actually causes problem for FoundationPose to generate accurate object poses. So with FoundationStereo, you can actually get near ground truth depth map with a low-cost RGB-D camera like RealSense. And this is truly a game changer. And we first published this project as a research project on GitHub in March, and we submitted a paper to CVPR 2025. This is actually one of the 14 Best Paper Award nominees out of over 10,000 submissions this year. So if you're using a low-cost RGB-D camera today, stereo camera, I would highly encourage you to check out this model on GitHub. And the second model we have is synthetic data. This is a transformer-based object detection model specifically for indoor and industrial environments. This model can detect objects very accurately, and it generates a bounding volume around each object it detects. And you can feed this bounding volume to FoundationPose as one of the inputs. So to use this model to detect your own objects of interest, we're also releasing a retraining microservice in Q3. So you will be able to retrain this model based on your own data, and it's able to detect your objects very reliably. And lastly, we also have BondoSDF. This is solving the problem that sometimes end users of the robotic system may not have access to CAD models or textured mesh files that are needed for FoundationPose. So the typical approach is to buy a very expensive 3D scanner, and you can scan your part and generate a mesh file, or you can send it to a service provider, spend a couple $100 on each scan, and you'll be able to get a mesh file back in a few days or even a few weeks. But with BondoSDF, you can simply capture a video of your object with your existing RGB-D camera, and BondoSDF is able to generate a textured mesh file within a few minutes. So once you have the pose estimation from FoundationPose, you can use another model called FoundationGrasp to generate feasible grasps given the gripper you're using. So say if you're using a two-finger gripper or a suction cup today, and you want to know how, the different ways of grasping a part, you can actually automate that process using FoundationGrasp. So this is a foundation model that you can train for your own gripper. And we will be releasing the training scripts and also the data generation pipeline in the upcoming months as well. So once you have perception, the next step is robotic motion planning and control. So cuMotion is another cornerstone of Isaac Manipulator. This is a GPU accelerated library specifically for robot trajectory planning. And we are leveraging the massive parallel computing power of GPU in this library. So if your robot needs to operate in a very cluttered environment, and you want to automatically generate trajectory, you can use cuMotion to do that. So in order to model your environment and obstacles, we also have another library called NVBlocks. This is a library that enables real-time scene reconstruction with your RGB-D cameras. So in real time, you're able to generate a signed distance field for your environment, and you can feed that into CrewMotion that will be able to generate collision-free path planning in a fraction of a second. So CrewMotion today was released as a component of Isaac ROS, which means you need to use ROS2 in order to use this library. But I'm very glad to announce that we are going to release a new version of CrewMotion in August. This will be a standalone C++ library with Python bindings, so it will be very easier for you to integrate this library into your own workflow. So if we're putting all the components together in one graph, this is what you get from end to end. You typically start with your RGB-D camera, capture environment and scene, and you send it to perception models, and you'll get object poses and target grasp poses, which you can later send to CrewMotion for execution. So CrewMotion will be able to generate collision-free trajectories that you can stream directly to your robot controller for execution. So like I said, synthetic data, CrewMotion, FoundationPose, NV blocks were all released about a year ago. And now we're adding the new CrewMotion library and also the retraining microservice for synthetic data. In addition, we're releasing the first commercial versions of FoundationStereo as well as FoundationGrasp and BondoSDF later this year, hopefully in the second half of 2025. So all the models and libraries here are optimized for our third computer. So you can download and use them on our Jetson platform as an example. We are very proud of working with a growing ecosystem of robotic companies. Here are just a few examples. Some of them actually have booths here this week, including Vention, UR, and TM Robots. I would encourage you to check out their booths and the demos and see these tools in action this week. So the best of all is all the models and libraries that I just mentioned are offered for free for commercial use on our Jetson platform and NVIDIA GPUs. There is no paid license or subscription required. And to get started, you can just simply visit our website and check out the tutorials, documentation, reference workflows, and you'll be able to get started very quickly. So if you have any questions or feedback, feel free to reach out to us through our user forum, as well as our GitHub page, and our developers and customer support personnel will get back to you shortly. With that, I would like to hand it over to Francois and Jimmy from Vention, and they will be sharing their experience of using NVIDIA technologies to build their new bin picking product. And it's a real pleasure to be working with them in the past few months and firsthand witnessing their amazing progress they've made so far. So Francois, I'll let you take over from here. Thank you.
Mic check. OK, very good. Thank you, Yichao. It was a pleasure to listen to your presentation and, of course, to work with you and the NVIDIA team. It feels a little bit strange to be here because, funny story, when I was in college, my nickname was the machine learning Grinch. And now that I'm here working with Yichao and with NVIDIA on stage pitching AI, it really feels like AI is really taking over the world. So thank you for spending some time with us. I will take some time also to introduce Jimmy now. He will do the second half of the presentation with me on stage. Jimmy is from McGill University, did his PhD over there and worked at Samsung as well. He's a fantastic AI developer and researcher, and it's been a pleasure to work with you, Jimmy, so thank you. He will talk about the nuts and bolts and the detail of how our technology works. So before getting into the details of MachineMotion AI, I want to talk about Vention a little bit because I recognize that some of you might not exactly know what we do. I want to take a little bit of time to explain so the rest of the speech makes a little bit more sense. So Vention is a digital platform to build machines more cost efficiently, faster, and easier than alternatives. So what we've done is two very simple things. We rebuilt the hardware for industrial automation, just a small side task, and then we built also a single digital thread of software online where people can go utilize these blocks to build machines. So people will build palletizing systems, bin picking systems, Cartesian robots, conveying systems on our platform. Now, where MachineMotion comes in is in the middle of this ecosystem of parts and of software. We need controls, and we built a platform especially to control all these devices and also to be GPU accelerated. So going back to the hardware and software, our platform allows customers to come in, go on our website, assemble their machines using our hardware. They can also program their machines online. They can simulate their machine, and when they're ready with they're happy with the results, they can order the parts, and we ship in to the customers next day. So going back to MachineMotion AI, and if you want to see it, I think you might be able to find the Vention booth around. I've heard it's not too far. You will see MachineMotion AI in the flesh. 20 months ago, when we started to build it, we contacted NVIDIA because we wanted this new generation. It's our third one. We wanted it to be GPU accelerated for a couple of different reasons that I'll talk about. So at the core of MachineMotion is an NVIDIA Jetson platform. We utilize it to do two very specific things. The first one, as Yichao pointed out, is on the dexterity and grasping side of things. I don't know if you recall on one of Yichao's slides, there was the Lego Jetson that was being grasped in different directions. This is grasp planning. This is a very important part of any cell in the world of robotics. You need to understand how you will grasp the thing that is ambiguous in front of you. So that's one of the very important things we have to do. The second thing is to make sure we perceive what needs to be grasped. So when we built MachineMotion AI, we knew we needed to step up our game in terms of autonomous robotics. So we focused on making sure we had the right platform, the right compute to do perception, so where is the part, and also grasping, how do I grip the part. But the other tricky thing is, the more ambiguous your environment is, the more delicate it is to move around. Because you, first of all, don't exactly know what you're going to pick, but you also don't know exactly where it is, and you don't exactly know how to pick it. And this is where advanced GPU-accelerated motion planning comes in. So with the GPU platform that NVIDIA offers, now what we can do is leverage tools like QRobo. Not only you can plan faster, but you can plan a lot more options. Again, remember the Jetson little Lego block. When it's in a bin, you don't really know what's going to make the more sense. So you use advanced accelerated motion planning to try many things in parallel, and whatever works best, you can utilize. So again, the reason why we selected to work with a GPU platform is for two core things: autonomous robotics, and there's the perception part, and there's also the grasping part, and finally, for advanced motion planning, to see the world in 3D and accelerate the path planning that we do with robots. So just to summarize, we took the Vention ecosystem. We can build machines online using the tools, using the hardware kit, using the software suite. And then we have MachineMotion AI at the center of the platform that gives you all the compute and the processing power you need to run your advanced software that's GPU accelerated. And then on top of this, you have your grasping, and then also you have your perception. Finally, you have everything you need to build what we are going to show you today. Jimmy is going to talk about more in details of the nuts and bolts and how it functions. But this is the GTC demo of a bin picking application that we are releasing later this year and doing pilot at customer projects with. What's special about this system is you can actually use foundation models that are powerful enough to spare you the very big effort of retraining every time a new part, because it consumes only a 3D model. Also, the grasp planning utilizes tools from NVIDIA, so you don't always have to go and determine how you're going to pick the parts. The system does it for you, and we remove the human in the loop. But without further ado, I'll have Jimmy jump on stage and tell you more about it.
Hello, everyone. It's a pleasure to be here today to talk about AI. So what you're seeing here is a bin picking solution that we first presented at GTC of this year. It's a pick-and-place solution, so we go from a very unstructured bin where the parts are just randomly placed and we're able to pick it up very precisely, and we do a structured placement. And over on the right side, there's a screen that shows what the robot is thinking. So it's showing the parts that the robot is considering. And the green one is the one that it has decided to pick. Okay. So today, I will give a brief overview of the technology behind this bin picking solution. And we make use of 4 key components from Isaac Manipulator, which Yichao has introduced. So we use FoundationStereo, FoundationPose, NVBlocks, and QMotion. Now, at a very high level, our pipeline starts by acquiring RGB images using a standard stereo camera. We give those images to FoundationStereo, which computes a very accurate depth map. Then that information is given to FoundationPose, which estimates the pose of the object we would like to pick. And then from there, we select the grasp, and we use QMotion to plan a path to grab that object and do the placement. And I will talk about these components in more detail. As Yichao mentioned, FoundationPose is a foundation model for estimating the pose of objects. And what's cool about FoundationPose is that it does not require any training to generalize to objects that it has never seen before. So all you need to do is give it a CAD model, and it will be able to estimate the pose of that object given an RGB-D image. So at the top right, there you see a CAD model of the part that was being picked in the video demo just now. And just based on that CAD model, it is able to detect the pose of the objects, which is what you see at the bottom right here. And since it requires no training to generalize to new objects, we call it a zero-shot model. And so being a zero-shot model, it translates to a very low effort to onboard new parts. And that translates to very fast deployment and a low cost of deployment. And over the past few months, we've tried using FoundationPose on a variety of objects that are all very different. And so far, we found it to be very robust. We've tried it in various kinds of lighting conditions, and is able to adapt very, very well. And so I've also had quite a few discussions with people about the need to do training. And so I think FoundationPose is kind of, so it gives us some evidence that maybe in the future, for a lot of applications, we don't necessarily have to train. We can use a foundation model. And if you think about it, if we train, there are actually risks associated with training, right? First of all, it's very time-consuming to generate the data. And then if you don't do it properly, you could overfit on the data, and it won't generalize during your, deployment. So you might end up spending all that time and effort and end up with a model that's not as good as, say, FoundationPose. So on the next slide, I have a video that shows the result of FoundationPose. So there in the red, we have a CAD model. So this is the output of FoundationPose. We have it overlaid on this point cloud here. Okay. So next, I will move on to talk a bit about FoundationStereo. I personally think that FoundationStereo is one of the most exciting technologies to come out this year. It allows us to produce very accurate depth maps from just a very cheap standard stereo camera. So stereo is the problem where you're given 2 images, and your goal is to compute the depth or the distance from the camera for every single pixel. Now, why is that hard? So if you look at this blue background here, right? I mean, it's just a bunch of blue. So if you have 2 cameras that are looking at this, you have a bunch of blue pixels in one camera and a bunch of blue pixels in the other one, and it's hard to know which pixel from the 2 cameras correspond. And if you cannot do the correspondence, you cannot triangulate. And that's why traditionally stereo is very difficult. But FoundationStereo solves this problem using AI. So you give the 2 images from the 2 cameras to FoundationStereo, and it outputs a very high quality depth map. And this is then used in downstream tasks. So for example, FoundationPose will make use of the depth. And also we use the depth to inform the motion planning part of the pipeline so that it can plan around the obstacles. So here we're showing a side-by-side comparison with and without FoundationStereo. At the top right, we are showing the output of FoundationStereo. As you can see, it's a very high quality depth map. And at the bottom right, you see what is typically you will find using traditional stereo techniques. And as you can see, it's very, very noisy. OK, so in this video, I am showing a demonstration of the power of FoundationStereo. Now, these white parts, you can see that there's not a lot of texture on it. So traditional stereo techniques will have trouble with this. But FoundationStereo can produce a very high quality depth map, which we then use to build this point cloud here. And I think this is very, very impressive. OK, next I will move on, and I'll talk a bit about QMotion and motion planning. So as Yichao mentioned, QMotion is a library for doing motion planning for robots. And what's special about QMotion is that it allows us to consider many paths simultaneously in parallel on the GPU. So why is this important for bin picking? So when you need to go into a deep bin, when the robot has to put its whole arm into a bin, its motion is actually very constrained. Okay? So typically, our approach is that when you're given an object that you want to pick, we want to have a large pool of candidate grasps that go at the object from all kinds of angles. Okay? And some of them will collide with the bin, and some of them will not. So we need a motion planner to kind of think through all of those possible grasps and find the ones that do not collide with the bin. And because QMotion is able to take advantage of the GPU to think through all those plans in parallel, it can do the planning very, very quickly. Also, QMotion, like most other planning libraries, it has the ability to plan around obstacles. And to do that, so we have another library called NVBlocks, which allows us to build a 3D representation of the world, which is then given to QMotion so that it can plan around the obstacles. OK, so next I will show a demo that kind of puts everything together. So in this pipeline, we start with FoundationStereo. We compute a high-quality depth that gets fed into FoundationPose, which is used to estimate the pose of the objects. From there, we use QMotion to plan a path and pick up this object. And the robot is able to very accurately identify the pose of the object, which enables this very precise place. We put it upright on the platform there, and it is able to also avoid hitting the bin. Yeah, here you can see it's going very close to the bin, but it doesn't hit it. OK. Here, what I'm showing is the input that goes into NVBlocks to build a model of the environment. So this is actually very much a demo of FoundationStereo. So to build this, what we do is we take our stereo camera, we move it around the environment, we collect a bunch of stereo images, we process all of them with FoundationStereo. So that gives us a bunch of point clouds. We put all of those point clouds together, and that gives us this massive point cloud, which we then give to QMotion to build a model of the environment. OK, so that's it from me. I think we can now open it up to some questions, and I'll invite the other speakers onto the stage as well. OK, thank you. So if you have a question, I think you can raise your hand and someone will bring you a mic. Yep.
Hi, I got a question about what's the output from QMotion? Is it generating joint values for the robot or Cartesian locations? And how does that integrate to the actual controller? Are you controlling the controller directly from QMotion, or is there another step?
Yeah, we do. We have 2 steps in the motion planning pipeline. There's always a planner and there's always a driver that ingests a stream of points, velocity, and positions in time. So we always output the same matrix, whether it's from QMotion or from another planner. It's always a list of points in time with velocities and acceleration. We also tweak certain things to limit the jerk sometimes. And after we take that matrix and we send it to the driver and it streams to the robot. So we use different drivers for ABB and for Fennec and for UR. They all have slightly different implementations under the hood, but essentially we want to use only motion streaming for the robots.
I have more of a hardware question. So computationally, there's a lot of decisions that are being made. One, maybe where are each decisions made, like which computational device, and like how many real computers are there functionally?
I struggled a bit. Did you?
Yeah, I also didn't really hear the question.
Can you hear me now?
Yeah, that's better.
Okay. So there are many decisions along the process that are having to be made in order to get that final output of picking up an object, right? And so I'm really wondering, where are the decisions being made? Are they being made on the local processor, or is there some sort of back end or computational device that makes the decision and then sends information to that local Jetson or whatever platform you're using?
Yeah, so I can answer that one. So the demo that you saw at GTC, that was fully running on board our embedded controller, the MachineMotion AI. But of course, during our development, very often we also run things in the cloud just to make sure that it works first. And then once things work, we put it onto our embedded device.
While training the, did you guys do comparison between using like the FoundationPose versus using like a traditional method of vision stack, and then using like synthetic data to train the vision model? Like how far off was the results with the FoundationPose?
Yeah, I'm sure if you look at like the FoundationPose paper, there will be information about that. So on our part, we started working on the bin picking solution sometime late last year, and our goal has been to deliver a product as quickly as possible. So we haven't done as much of that kind of benchmarking as we'd like so far. Yeah. So yeah, to answer your question, no, we have not tried training the other models to compare with FoundationPose.
But the big difference, if I may, is the fact that standard training is not ideal, right? Like every time you train, you deploy human resources, human capital, it takes time. The great thing with FoundationPose is because it's a foundation model, you feed it a 3D model and you can onboard new parts very fast. So for us, this is the part we found extremely appealing with FoundationPose, is the time to onboarding a new part is really, really low. And in our industry, you go on a factory floor, you always have different parts. Nobody manufactures the same stuff, right? Like every bolt is a different bolt, right? They're all special. So like if you go to a factory floor and you want to do bin picking and you want to pick an unstructured, in-feed of parts, you need to be able to onboard part quicks. Otherwise, the projects are too long and are not economical. So this is really, like even if it's a little bit less precise, and I don't know, maybe it's even more precise, but in our case, it mattered less, right? We wanted the speed of onboarding parts.
Yeah, and if you're interested in the performance of FoundationPose, you can also check out the public leaderboard because we've done a very extensive testing of FoundationPose using the publicly available benchmarks. So you can see how FoundationPose performs against other pose estimation models online. All the data is public, and you can even validate the performance by following the scripts available.
My boss might want to ask when everything is ready and commercially available. Then.
So I'm curious about the foundation pose. So if you have multiple CAD files, so say you have 20 different parts, and you put those parts in the bin, it's going to recognize the position of each one of those parts.
Yeah. So Foundation Pose requires you to give it a region in the image to analyze. Okay. So typically you don't use Foundation Pose just by itself. So usually you have something in front of the Foundation Pose, like an object detector, that tells you which part of the image to focus on. So you give that to Foundation Pose, and yes, you have to specify which CAD file should be used for it. So ideally, your object detector that runs before it tells you both where it is in the image and also what it is, and that can inform Foundation Pose as to which CAD file to use.
Yeah, but you'll be able to switch CAD files on the fly. So once you finish detecting one part, you can quickly load another CAD file and do another detection. And if you run everything on a very powerful GPU, you will be able to get results quickly as well.
So you basically have several models that you use when is the right time. You can switch dynamically. And for our use cases, they've been mostly, you have one bin with the type of parts, you run the model, the bin gets changed to another part, reload the next model. They could be mixed back, but we haven't done this so far. So that's the target.
Which part of the process is the most computationally taxing?
Yeah, so currently our pipeline is fully zero shots. Okay, so we don't do any training. And so for the detection phase, we actually use some other foundation models from Meta. For example, we use segment anything. And so far, that has been the slowest part. Yeah, Foundation Pose is, so Foundation Pose can be run in different modes. So there's a full registration mode where there's no prior information. You just use Foundation Pose to estimate the pose of the object. That one can be heavy. That one can be a bit slow. But there's also like a tracking operation where you give it a prior. Then in that case, the Foundation Pose can run much more quickly.
Yeah, simple question. I have an NVIDIA chip on my laptop. Will QMotion work with it?
Yes, I think as long as you install the right drivers that's compatible with QMotion, you should be able to run it on discrete GPUs. Yeah, and if you want to try out all the components quickly, you can install ROS on your computer. And we have reference workflows that are compatible with ROS 2, so you'll be able to get everything going very quickly that way.
And it's really impressive. Honestly, I highly recommend it. Like the plans that QMotion and QRobo are capable of generating are truly impressive. It's very great.
I think it was called Boundless SDF or something like that?
BondoSDF.
Yes. So that you're taking an RGB image and converting that into a 3D model? Is that correct?
Actually, you need to input a RGB-D video or like a series of RGB-D images. Yeah, BondoSDF will be able to convert all the data into a textured mesh file.
Interesting. Okay.
Hi. So for the FoundationGrasp, I have a question. So for the Lego, right? So it's capturing that model, right? And then let's say you have a bunch of Legos, and the robot is it grabbing. When it chooses, is it choosing just out of like the shape? Let's say, because there's a lot of them. So is it choosing, let's say, like the hand? It knows that that is a specific Lego. And let's say you have like different types of Legos. Like, how does the program like see or choose between that?
Yeah.
So the output of FoundationGrasp is a set of all feasible grasps given a pair of object and gripper. So you say you have a two-finger gripper, you have your object, and in simulation, we were able to simulate probably thousands of feasible grasps for that particular pair. And during runtime, you have your own orchestrator that needs to make a decision, like which grasp to execute. That's probably based on your motion planning results as well. So you can use CoolMotion to validate some of the grasps in a particular orientation. And based on the results, you can pick which grasp for execution.
Right.
So FoundationGrasp doesn't tell you directly which grasp is the best because it needs to take into other factors into account.
All right.
Okay. All right. Thank you, everyone.
Thank you, everyone.
Yeah.